Welcome to Wings of Arrow Advanced Education and Research Organization. To know more, visit our official webpage www.wingsofarrow.in. Find your dream aviation and aerospace jobs at www.wingsofarrow.in/jobs. Now we are going to learn how to find the power required to drive the reciprocating compressor. Consider a reciprocating compressor that delivers 5 kg of air per minute at a pressure of 7.5 kg force per centimeter square. The pressure and temperature of the air before compression are 1 kg force per centimeter square and 15 degrees Celsius respectively, and the compression process may be assumed to follow the law PV power 1.2 equals constant. If the rate of heat transfer from the cylinder is estimated to be 1.6 horsepower, calculate the power required for the compression. Take C suffix P is equal to 0.24. Here we consider reciprocating compressor. Let me write the given data. Mass rate of air per minute m is equal to 5 kg. Pressure of air after compression P2 is equal to 7.5 kg force per centimeter square, and pressure of air before compression P1 is equal to 1 kg force per centimeter square, and temperature of air before compression T1 is equal to 15 degrees Celsius or 288 Kelvin, and rate of heat transfer Q is equal to 1.6 horsepower, and specific heat at constant pressure C suffix P is equal to 0.24. Now we have to find out the power required for the compression. So a reciprocating compressor or piston compressor is a positive displacement compressor that uses pistons driven by a crankshaft to deliver gases at high pressure. So reciprocating compressors are primarily used in industrial manufacturing plants and for on-site work. Required power to drive the compressor depends on the rate of heat transfer and ideal enthalpy. Then we can write total power required is equal to mass rate into C suffix P into T2 minus T1 plus heat transfer, where mass rate is given and specific heat constant pressure is also known. T1 is the temperature of air before compression, which is also given. We know rate of heat transfer, and T2 is the temperature after compression, which we don't know. So first find the temperature. In fluid dynamics, an isentropic flow is a fluid flow that is both adiabatic and reversible. For an isentropic flow of a perfect gas, several relations can be derived to define the pressure, density and temperature along a streamline. So from isentropic relation we know that T2 is equal to T1 into P2 divided by P1 to the power n minus 1 divided by n, where T1 is the temperature before compression, P1 and P2 are the pressure before and after compression respectively, and n is the polytropic index or exponent. An ideal isothermal process must occur very slowly to keep the gas temperature constant. An ideal adiabatic process must occur very rapidly without any flow of energy in or out of the system. In practice, most expansion and compression processes are somewhere in between, are said to be polytropic. So the polytropic process can be expressed as PV power n is equal to constant. So for this problem n is equal to 1.2. Now substitute those values and solve. We get T2 is equal to 403 Kelvin. Now we can find out the total power required. Solving equation number 1 with known values, we get the required power. Keep in mind that 10.54 kilocalories per minute is equal to 1 horsepower. Then to get the power in terms of horsepower, divide 10.54 kilocalories per minute. Thus the required power for reciprocating compression is 14.7 horsepower. Did you know? A 95% illuminated moon appears half as bright as a full moon. Believe it or not, the moon is half as bright as a full moon about 2.4 days before and after a full moon. Even though about 95% of the moon is illuminated at this time, and to most casual observers it might still look like a full moon. Its brightness is roughly 0.7 magnitudes less than a full face, making it appear one half as bright. We all know there was a man on the moon, but did you know that there is one who stayed there? Dr. Eugene Shoemaker, a geological surveyor who educated the Apollo mission astronauts about craters, never made it into space himself, but it had always been one of his dreams. He was rejected as an astronaut because of medical problems. After he died, his ashes were placed on board the Lunar Prospector spacecraft on January 6, 1999, which was crashed into a crater on the moon on July 31, 1999. The mission was to discover if there was water on the moon at the time, but it also served to fulfill Dr. Shoemaker's last wish.
If you have further inquiry or requested video, drop down to our mail wingsofarrow@gmail.com. Don't forget to subscribe for more updates. For the time being, take care, stay blessed, inspired and fly high.